So today we are going to solve moles problems for IB chemistry. This particular lesson would also work for A-level chemistry, so just everyone's welcome. Okay, so let's dive right in. First question. So at first I would solve multiple choice questions, which is paper 1, and then at the end there would be paper 2 questions. And the SL means that it's for a standard level, HL for higher level, but I think for this topic it's only SL questions we have. Yeah, because the point structure 1.4, it's the same for SL and HL. There is no additional HL content. If I think that's right. Okay, so first question. A compound of molar mass 92 grams per mole contains 12 grams of carbon, 2 grams of hydrogen, and 32 of oxygen. What's the molecular formula for the compound? Okay, so first what we do is we find empirical formula. Because this is a multiple choice question, we can round the molar masses, so I don't have to use 12.01 for carbon. Yeah, it's strictly speaking, you have to use 12.01 if you're solving paper 2, but here I will just use it as 12. Okay, so carbon is 12 divided by 12, so I'm converting all the masses into moles because my goal is to find the molar ratio of atoms. Yes, okay, that's streaming. Okay, just double checking. All right, so carbon is 12 grams, hydrogen is 2 divided by 1. 1 is the molar mass of hydrogen, again rounding because it's a multiple choice question. Then oxygen, 32 divided by 16. And then I calculate what that is, so it's 1, 2, and 2. That is, it means that the formula, the empirical formula would be CH2O2. C1, yes, C1, which I don't have to write. H2O2, that's the empirical formula. And then to find the molecular formula, we need to use 92. Yes, so they've given us the molar mass of the compound, so we just have to find out how many times heavier is our molecular formula compared to the empirical formula. So what I'll do is I'll find the MR of the empirical formula that I got, CH2O2, which is, well, 12 plus 2 plus 16 times 2. Yeah, well, I'll write it down. 12 plus 2 times 1 plus 2 times 16, which is 46. And then I do the true molar mass, so 92, and divide it by 46. It should be 2, right? I don't trust my mental math, so I'll just double check. Yeah, that's 2. So we have to have a whole number. If you didn't get a whole number at this stage, something is wrong. You have to double check your divisions and so on. Okay, so I got 2. It means that I have to multiply all the indices, yes, so all the small numbers by 2. So it would become C, instead of C1, it's now C2, H, it used to be 2, now it's 4, and O4. That's the molecular formula. So the answer is D. Molecular formula. Okay, just be careful with these numbers. If you didn't get good whole numbers, then you have to think, yeah, you maybe have to multiply by something to get whole numbers and so on. So don't round them too early. So for example, if you get 1.5, you keep it as 1.5 and not as 1 or 2. Yeah, then you just have to multiply by 2 to get 3. Next question. Ethanoic acid has the formula CH3COOH. How many carbon atoms are present in 0.1 moles of ethanoic acid? How many carbon atoms are present? Yes, so what do we need? We need carbon atoms. So first I find the number of moles of carbon atoms. So it's 0.1 times 2, because each molecule of ethanoic acid has 2 carbon atoms. Right, so I do 0.1 times 2. This is the moles of carbon atoms. And they didn't ask me about the moles, but they asked about how many carbon atoms, so I have to multiply it by Avogadro constant. Yeah, so if they asked me about the moles, then it would have been just 0.2. That's the moles of carbon atoms. And that is times 10 to the 23rd. Now you're allowed to use the calculator, you know, right? So it's B. 1.2 times 10 to the 23rd. Next question. A hydrated carbonate of an unknown group 1 metal has the formula X2CO3 times 10H2O and is found to have a relative formula mass of that. What is the group 1 metal? So when you have a crystalline hydrate that looks like this, yeah, so you have, well, a salt, like a carbonate or some other salt, and then it says times some H2O. So this times, it's usually very confusing. So it just means that you're adding, yeah, you're adding 10 water molecules to the molar mass of X2CO3. Well, let's set the molar mass, the relative atomic mass of the metal X as X. Yeah, let's just do that. And then I will write down the molar mass of this whole salt. So Mr of X2CO3 times 10H2O, it would equal to, so I will use here the decimal, yeah, so it's a molar masses with decimal points to 2 decimal places, just because they gave me molar mass to some decimal places so that I don't get the weird number for X. Okay, so let's calculate. So I have 2 atoms of X, so it's 2X plus 1 carbon. Carbon is 12.01 plus 3 oxygens, 3 times 16. That's all. 16 is from the periodic table. Plus 10 times 6 molar mass of 6 water molecules. So you do 10 times 10 times molar mass of a water molecule. So 2 times 1.01 plus 16. Yeah, that's the water molecule. And then it's 2x plus, and then I just add up all those numbers. So 12.01 plus 3 times 16 plus 10 times, this is what, 18.02, that's water, right? That's 240.21. And I know they gave me the value for the molar mass, so that molar mass equals to 286.19. Okay, let's see. So it means that 2x plus 240.21 equals to 286.19. So from there, x would be 286.19 minus 240.21 over 2, which is 22.99. 22.99, so that's the relative atomic mass. Yeah, the relative atomic mass of the metal X. We know it's in group 1, well, and it is sodium, right? So 22.99. There it is, sodium. So the answer is C. Okay, next one. Question 4. A coin contains 5.6869% of nickel by mass. If the coin weighs 10 grams, how many nickel atoms are in the coin? Okay, so we have a coin. It's a mixture or like an alloy of nickel with something else, and we need to find out how many atoms of nickel are there. So first we will find the mass of nickel, then the moles of nickel, and then the number of atoms. So first the mass of nickel, it's 5.869% out of 10 grams, so I do 10 times 5.869 over 100, which is 0.5869, right? 869 grams. 869 over 10. And then I find the moles. That's mass over molar mass, so 0.5869 divided by, relative atomic mass of nickel. It's, where is it? 58.69. Yeah, this one. 58.69. So that is 0.01. 69, yes, that's 0.01. And then we find the number of atoms. Right, the number of atoms, it's moles times Avogadro's constant. .02 times 10 to the 23rd, so that's 6.02 times 10 to the 21 atoms. That's a D. Good. Okay. Next question. Which sample contains the largest amount in moles of atoms? Largest amount in moles of atoms, so we just have to find out the number of moles of atoms in each option. Well, let's see. So just the moles, right? We don't have to find the number of atoms, but actually, even if they asked to compare the number of atoms, we could still compare moles, because to convert between moles and the number of atoms, you just multiply by Avogadro. So if you have more moles, it means that you would have more atoms. So the substance that has the most moles would have the most atoms as well. Okay, let's see. So which sample contains the largest amount of atoms? So for A, I do 0.30 times the number of atoms in a molecule. So in P2O5, we have 2 phosphorus, 5 oxygen. So 2 plus 5, 7. 7, so that is 2.1 moles of atoms. Now for B, it's 0. Oh, B looks like it could be B, but let's check. So 0.40 times. Okay, so how many atoms do we have? From CuSO4, so we have 1 copper, 1 sulfur, 4 oxygens. It's 6. And plus 5 water molecules. In each water molecule, there are 3 atoms, 2 H's and 1 O. So 5 times 3 plus 6, 21. 0.4 times 21 is 8.4 moles. Okay, that's a lot of moles. Then for C, it would be 0.50 times, how many atoms do we have? 4, so 1 C, 3 H's, it's 4, another C, 5, 6, 7, 8. 8, right? 4, 7, 8, yes. 8 times 0.5 is 4. And then for D, 0.90 times 3, because there are 2 H's, 1 oxygen, so 2.7. Okay, so yes, it is B. Yep, it is B, because there are so many atoms in one formula. Right. Next one. How many ions are present in 0.02 moles of NH4 3PO4? This is the question that a lot of students find difficult. So you need to count the number of ions, and you just have to know that NH4 plus is a cation, PO4 3 minus is an anion. We do it when we do bonding, and I think it's structure 2. So if you don't know it yet, if you've just started the syllabus, it's okay. But well, usually I make my students memorize the table. If you're watching, if you're watching, you know, it's so the table with all the cations and all the anions that you need for the exam. Well, NH4 plus and PO4 3 minus are 2 of those ions that you will recognize by the end of the specification. So in this formula, we have 3 NH4 plus cations, ions, and 1 PO4 3 minus, that's an anion. Yes, so in total we have 4 ions, 3 plus 1. Yep. So we need to know how many ions. So I do 0.02 times 4, that's the moles of ions, and times Avogadro's constant. Okay, 0.02 times 4 times 602 times 10 to the 23rd, which is 4.8 times 10 to the 22nd, which is C. C. Next one. Right, now open response questions. Mercury forms 2 oxide, mercury 1 oxide, and that's Hg2O. I'm always writing the formulas because that's easier to read then. And mercury 2 oxide, the 1 and 2 show the oxidation states on the metal. Yeah, so this one is +1, this is +2. Oxygen and oxides, it's -2. Which decomposes into their elements when heated above 500 Celsius. After heating, we have 4.513 sample of an oxide of mercury, and 4.180 grams of mercury was left. Determine the empirical formula of this oxide. All right, so to find out the empirical formula, so what do we know? It's heating. Yeah, so we're heating an oxide, so either this one or that one, and when it decomposes, well, it forms mercury, and the rest of the mass must be oxygen then, right? Because we still have our law of mass conservation, or whatever it's called. So it's it means that the total mass of the products equals to the total mass of the reactants. So from here we know that the mass of mercury is 4.180, and then the mass of oxygen would be the total mass of the sample minus mercury, because oxide is just mercury and oxygen. So 4.513 minus 4.180. And then once we know the masses, we'll find the moles and find the ratio. That's 0.333 grams of oxygen. Right, now I convert it to moles, so I do mercury would be 4.18 divided by molar mass. Okay, where is it? Hg. Can't find mercury. There, 200.59. 200.59. And oxygen is 0.333 over 16. Which is, okay, so this is 0.02084, and this is, well, approximately the same, 0.02063. So you got two numbers, then you divide by the smallest number, so by 0.02, but of course you see that it's 1-to-1 ratio, yeah, so it means that the oxide would be HgO. If we got 2-to-1 ratio, would have been Hg2O. Yeah, so that's the empirical formula. Next, formulate two equations including state symbols to show the decomposition of the two oxides of mercury. Okay, so well, apparently we would get mercury and oxygen. So Hg2O, including state symbols. I'd say this is solid, and then you for mercury. Well, mercury, it's a metal, right? But it is liquid, so that's like a weird metal that exists as liquid at room temperature. And O2, and so you put a 2 here and 4 here, and oxygen is gas, obviously. And another one with HgO, you go into Hg liquid and O2 gas, so I put a 2 and a 2. Next, another sample of the same mass of mercury oxide in part A was heated and gave a lower mass of mercury. Lower mass. Suggest why less mercury could have been obtained. This is the type of questions that everyone finds difficult, because it's the like lab-based question, right? So you do some experiment, and then they ask what went wrong in this experiment because you got a little smaller or higher amount of something. Yeah, so here we got less mercury. What could have been the reason? Well, it's possible that mercury oxide hasn't fully decomposed. Yeah, that's one reason. So I think that's the most common reason, because what did they do? They just heated it, yeah, and they got mercury. So yes, because it's liquid, we definitely see when the oxide has turned into a metal. So I would say yes, it's just 1 mark. So let's just say that it was incomplete decomposition. Yes, so some oxide has been left. Not all oxide decomposed. If it was a solid metal, then it would have been a bit more difficult, because it's possible that it would kind of mix with the solid oxide, and then it would appear that the total mass of the solid is higher. But here it's liquid, so we can tell when the mercury is formed. And then suggest why repeating the decomposition of the sample of mercury in part A may give a higher mass of mercury than was obtained in part A. So this was a lower mass, yeah, and now they ask what could happen if we got a higher mass of mercury. Well, it would be possible if, for example, we had if we had impure mercury oxide. So if instead of HgO we also had Hg2O, which has twice as much mercury. Yeah, so if it was contaminated with Hg2O, then we could get a higher mass. So contamination with Hg2O, which means that there is more mercury in that oxide. Yeah, so we would get a higher than expected mass. Right, next one. The open chain structure of the sugar galactose is shown in figure 1. Determine the empirical formula. Okay, so if I count all the atoms, I would find the molecular formula. Let's do that. So I have 1, 2, 3, 4, 5, 6. So 6 carbons, and then oxygens 1, 2, 3, 4, 5, 6. I mean 6. O6 and H, well, was it 12? Let's check. 1, 2, 3. Actually, I missed one. So, okay, so 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, H12. So it means that empirical formula would be COH2. Right, so you're canceling the indices. Oh, maybe you don't see what I'm writing. So you're canceling the indices out by 6, and don't leave it like that, okay? So because they ask for empirical formula, you have to cross this out. So you kind of calculate, but as an examiner, if I see both answers, like this answer negates that one. So if you leave it like this in the exam without crossing out, you can be marked off. Just a warning. Next, calculate the percentage composition by mass of galactose. Well, for that one, we do need the formula actually, C6H12O6, I just calculated. And to calculate percentage by mass, so percentage of carbon atoms would be the mass of carbon atoms divided by the total mass, right? So if I say that I have 1 mole of that galactose, it means that I have 6 moles of carbon. So I do 6 times 12.01. 12.01, it's the carbon, yeah, divided by the total molar mass. The total molar mass, I'll just calculate, I don't have space actually. Okay, I'll just calculate it once. So 12 times 1.01, that's hydrogen, and 6 times 16, that's oxygen. So you do, and times 100%. Yeah, so number of carbon atoms times relative atomic mass divided by the total molar mass. 12.01, that's 72.06, divided by 6 times 12.01 plus 12 times 1.01 plus 6 times 16, that's 180.18, and times 100%. Yes, okay, 72.06 over times 100, that is around 39.9. Oh no, yeah, 39.99, so 40%. 40%, then percentage of hydrogen would be 12 times 1.01. Now I know the molar mass, over 180.18. I'll just double check the MR. Yeah. Over 180.18, that's 6.73. Well, and oxygen must be the rest, right? So you can just subtract 100 minus 40 minus 6.73, but I'll calculate and see if it adds up to 100 just to double check. So it's 6 oxygen, so you do 6 times 16 over 180.18 times 100. 6 times 16 over 180.18, 53.328. Well, yeah, something is with rounding. Let's put it as 53.3. It's almost 100, right? 73 plus 53.3 plus 40. Yeah, so like I have to put this as maybe 6.7, and then it will add up. No, it's not. Oh wait, 53.3 plus 7.6 plus 40. Yeah, then that's 100. But I mean, you could leave it like that. It's fine. You could either leave it as 6.73, or you could just take more significant figures in these percentages. Okay, and you don't mark, you won't be marked off if you leave it as 3. In IB, there is a tolerance of 1 significant figure, so It should be fine if they haven't changed it this year. This year. So always double check the year when you are taking the exam. Fine. And then next one, formulate the balanced equation for the complete combustion of galactose. Okay, so complete combustion C6H12O6. What do? We are combusting it in oxygen, and the products of complete combustion are CO2 and H2O. They didn't ask for state symbols, that's why I won't be writing state symbols. They didn't, yes. Okay, and when we balance combustion equations, it's a good idea to balance carbon first, then hydrogen, then oxygen. So in that order, C, then H, then O. So first I balance carbons. I have 6 on the left, so I put it 6 in front of CO2. Then hydrogen, I have 12, so I put a 6 in front of H2O. And oxygen, so on the right side, I have 12 plus 6 is 18. And here I already have 6. So 18 minus 6 is 12. So I have to put a 6 here to make it 6 plus 12. It's also 18. So that is balanced. All right. I hope that's fine. And yes, you can send me messages, right, if something is not clear. There is a delay, but I'll be able to see them. Fine. Okay, next question. I think that's the last one. Is it? No, it's not, but we'll see. Oh no, it's not the last one. I have quite many questions, but not much time. So let's actually maybe choose one. This is what this we could skip, I think. Let's just take something. Yeah, let's do one combustion question. Let's do that one. Number 9. Okay. So carbone is an organic compound containing carbon, hydrogen, and oxygen. Complete combustion produce of that amount of carbone produces 0.4470 grams of carbon dioxide, and that amount of water. Determine the empirical formula. Show your working. So this is the combustion analysis question. Yeah, we did it once in the previous stream for IB. Right, let's see. So in this question, what do we do? So we need to understand that if you have a carbone, well, it does say that it has carbon, hydrogen, and oxygen, so you know, but they didn't have to tell that. Yeah, so they could just say that it's just some organic compound. Then you'd have to check whether it has oxygen or no. So I know that it does have oxygen, so I will just write it like this. And I know that upon complete combustion, it gives me CO2 and H2O. So all the carbon atoms from the carbone turned into CO2. All the hydrogen atoms from the organic compound went into water. We cannot say the same about oxygen because we added extra oxygen, right? So for oxygen that does not work. And so my goal here is to find the number of moles of carbon, number of moles of hydrogen, and number of moles of oxygen atoms, and then take the ratio. The ratio would give me the empirical formula. Okay, so first I find the number of moles of CO2, so that's mass over mR, which is 0.4470 divided by mR of CO2, so that's 12.01 plus 16 times 2, so 44.01. 447 over 44.01, which gives me 0.01016 moles. Then yes, and then we find the number of moles of carbon atoms. So in one molecule of CO2 there is one carbon, in one molecule of CO2 there is one carbon atom. So it means that the number of moles of carbon atoms equals to the number of moles of CO2. So that's the same. All right, and this number I will highlight. I will need it for my... That's an ugly color, actually. Let me choose another color. Okay, so this number I would use for the ratio, so I keep it. Then I do the same for water. I find water molecules, number of moles of water. So I have how much water? 0.1281 divided by molar mass. Molar mass was 18.02 from the periodic table. 81 over 18.02 is 7.1 0.09 times 10 to the negative 3 moles. Okay, that's the number of moles of water molecules. The number of moles of hydrogen would be twice as much because each water molecule contains 2 H's, right? So number of moles of H would be that number times 2, which gives me 0.01422 moles. Okay, that's fine. We found the number of moles of H and C. I will also highlight this number. I will need it for the ratio at the end. And then finally, I need to deal with oxygen. So how can we deal with oxygen? We cannot do the same for oxygen because, as I said, we've added extra. So the oxygen in CO2 and H2O, it's not just the oxygen from the molecule. But what can we do? We know the total mass. Yeah, we know that the mass is 0.1526. And the total mass, it's the mass of carbon atoms plus mass of hydrogen atoms plus mass of oxygen atoms. So I will just find the mass of carbon atoms, add the mass of hydrogen atoms, and then subtract 0.1526 minus the mass of the carbon and hydrogen. That's what I'll do. So mass of carbon, it's 0.01016 times 12.01. That's moles times MR. 0.1016 times 12.01, which is 0.1220 moles, grams. Mass of hydrogen, it's moles times relative atomic mass, which is 0.01436 grams. And now, if we've done everything correctly, we should get some mass left for oxygen. Well, let's check. So we have that is the amount. Yes, so 0.1526, that's the total mass. And then I subtract carbon and subtract hydrogen. So the remaining mass should be the mass of oxygen. Okay, let's see. 1526 minus 12.2 minus 0.01436. That is 0.01624 grams. Okay, yeah, so it's not a zero, looks good. Then we find the moles of oxygen. It's mass of oxygen over relative atomic mass. Over 16, that is 1.015 times 10 to the negative 3 moles. Right, and that's the last number that I need for the ratio. That's my last number, and then let's take the ratio. So I do moles of carbon to moles of hydrogen to moles of oxygen, so it would be 0.01016, that one, to 0.01422. So now I'm using my highlighted colors, yeah. 15 times 10 to the negative 3. So I got the ratio. It's not whole number, so I divide all the numbers by the smallest, so by this one, and I get, so 1 from here. Now 0.01016 divided by, so by the smallest, yeah, so by this one. This is 10. 0.1422. And this is 14, so that's perfect. Yeah, so we got whole numbers. We don't have to do anything else. And so it means that our empirical formula would be C10, yeah, because the first one was carbon. The next one is hydrogen, H14, O1. So just O. And that's it. That's the... Do we need anything else? Determine the empirical formula showing you're working. Okay, yeah, that's it. Nothing else. Let's see if we have time for this question. Vaporized, and what about this one? And okay, this one we definitely won't do, but let's do this one. Let's try to do it quickly. 2 marks should be pretty quick. A 0.146 gram sample of carbon when vaporized had a volume of that at 150 Celsius and 100.2 kilopascals. Calculate the molar mass showing you're working. The conditions are not standard. You see, 150 Celsius is not a standard condition. A pressure is also kind of not very standard. And that's why we're using the ideal gas equation. So we can find, what do we need? We need the molar mass. Okay, so the ideal gas equation is PV equals to nRT. From the ideal gas equation, we can find moles, right? We can find moles. So I rearrange it to find moles. And then I would know the mass and I would know the moles, so I can find MR. So first moles, PV over RT. Okay, guys, and now if you are doing A level, you have to remember that in A level, the pressure can only be in pascals and the volume can only be in cubic meters. That's it, there are no other options for A level. I lost the mark myself when I used kilopascals and decimeters cubed, which would give you the exact same number, but it's just for some reason they do not allow it, although we are kind of trying to change that. But as of now, you are not allowed to use anything except for pascals and cubic meters. If you are doing IB, it's okay to use cubic decimeters together with kilopascals, okay? And kilopascals and cubic decimeters, right? So you either use this set or this set, but you never use Pascal and dm cubed, for example. But again, for A level, only pascals and cubic meters. Okay. Right, well, let's see. So pressure 100.2 times volume 0.03. They're so nice. The units are all correct except for temperature. R is the gas constant, 8.31, and temperature, we have it in Celsius. We need to convert it to Kelvin, so it's 150 plus 273, which is 423 kelvins. And remember, it's 150 plus 273 gives you kelvins. Times 423. This would give me moles. All right, let's see. 423, yes, 100.2 times 31 over 423. That's 9.72 times 10 to the minus 4 moles. That's the moles. And now we also know the mass. Yes, we also know the mass, so I use the formula that molar mass, it's mass over moles. So I do 0.146 divided by 972 times 10 to the negative 4. And now the number should be sensible. Let's see how much we get. 0.0000972. Yes, so the molar mass that I got is 150.2 or just 150. That's grams per mole, right? And this is a nice number because it's not too large and it's not too small. If you get something like 0.1 or 10, that's too small for carbon, because obviously we saw that its empirical formula already has 10 carbons, right? If you got something like 20,000, that's too high. Yeah, so if you get a either very large or very small number, it means that you've messed up the unit somewhere. Yeah, so go and double check your unit. Okay, I think we'll stop here. So next stream would be for A level, I think organic A level chemistry. Right, okay, see you next time. Take care, everyone.